as you can see, this is way back in section 1.3. Am I going to ask you to reprove this? No. Basing on the looks of my other classes, are you going to understand this? Maybe. I mean, it's not an easy proof. And proofs, if you remember identities in pre-cal, what did you do? You just tried something until it worked. And that's the problem with proofs, is most students don't even know where to start. So I'm going to kind of throw some of that in there. But don't think you have to reprove this. I want to get to the end and say, okay, now there's the formula. Use it. For those of you that are really interested, can dig further into the proof in one. Two definitions that I'm going to say just use them when we get to the end of this, and we're going to see where they came from. What I want to do first is I want to actually prove these, okay? And so the first thing I say, well, how would I prove something like this? Well, I see theta and I see sines, cosines, so I think, well, what was pre-cal all about? Unit circles, you know, right triangle, you know, trigonometry. And so what I would like to do is maybe come up with a way that I can get these values based on just some particular angle. Now, drawings, the scaling is horrible. That looks like a football, not a unit circle, right? Okay, all right. So the scaling's pretty bad. I don't know why I couldn't get a perfect circle. And if you know they're a very good band, if you got that reference, then you're as old as I am. I don't think they're an old band, though. They're not that old. Well, you're old. Shut up. All right. So, so anyway, I have my... You're welcome. I have my circle here. I know what that point is. Why do I know what that point is? It's a unit circle. So I know I went out a distance of 1. I'm going to throw another point out here, radius, because they give, so somehow I need an angle. And you have no idea how long it took me to try to get that kind of where it didn't look ugly. And it still looks ugly. All right, so my eyeball looks at this and I said, wouldn't it be a perfect world if I could make a right triangle? Well, shoot, that's going to be easy to do. But I need to kind of know some of these other things. Hopefully, and you know, all this stuff you may not remember, but hopefully you kind of remember how to find arc length. Okay, that was your radius times your angle, r times theta. In this case, our radius is 1. So we're saying that this arc length is theta. And in other words, the absolute value. And this is where I say the scaling gets horrid, okay, because that doesn't even make sense by looking at it. But what we're going to use later is we're going to use this that says if I draw a line from here to here, that line must be less than that arc length, because if I took that arc and stretched it out, it's going to be longer than that line. Okay, just bear with me. I need this later, is why I want to know that. All right, so I told you what my mind would do is try to make a right. So that's what I do. And now that I have a right triangle, let's go back to the very first definitions. There were things with sines, cosines. Well, we all know the Sokotoa song, right? So I can figure out ways to cosines in here because I know my opposite over my adjacent. Okay, so if I'm looking at my opposite, I know. And don't forget that this entire thing, because I'm going to actually be interested in this triangle, is what I'm going to move to, is if this piece, if this piece is, there's my angle, is my adjacent, is my cosine, if all of that's to 1, then that piece right there has to be 1 minus cosine. Okay, so that's just where the values are coming in. Now, I picked this up. I thought, how cool would it be if I could make this animated and go to there? I picked this up, and I'm only going to be looking at triangle. We know that both, and so I have a triangle here. I'm interested in this piece. We know that by Pythagorean theorem, we could find that piece. We also know, of course, I'm squaring these, but you saw by the picture, the stuff was in quadrant 1, but we know that my sine and my cosines are going to be positive. And so I also know, because of this definition that I gave you a few slides back, I also know that this piece and this piece, I mean, if I'm going to take this and this, is going to be less than that AP. And so, which implies that both this piece and this piece is less than it. This is where we go back to, do you remember? If this is square and you square root it, we get very lazy with square roots. When you take square roots of stuff, do you do the absolute value? Yay, good students. Most students don't, they get lazy. And that's all I did here was when I took square roots, you're really supposed to do absolute values. And then do you remember inequalities? What do you do with this theta? Plus or minus. Very good. And end up with our definition. So there's the ta-da. Again, if you're staring at that going, I don't have a clue what you did. If you care, then I certainly would go through 1.3, try to go draw it on your own. If not, then you're the student here, just use it because I said to use it. Okay, so we're going to use this definition. In fact, we're going to use it with the sandwich theorem to find, because this is very important to find like what the limit of the sine is as our angle approaches 0. All right, so again, that's all in Blackboard, those slides. What can I call this? Sine identity.